Hello students. Now in this video we'll be talking about gyroscope. So as I told you earlier that gyroscope is actually uh, is a mechanical device which where we actually take help of the gyroscopic effect, okay, in some of our applications where like suppose taking turn, okay, in two-wheelers, right, and then taking turn in aircraft, ship, etc., okay, right turn, left turn, and going forward, backward. These things, the gyroscopic effects helps us, okay. So we need to understand what is this gyroscope, right? So here it is a mechanical way of maintaining orientation and angular velocity with the help of gyroscopic effect. We have to understand this effect here. This thing I have already told you earlier, but let's see. We have a shaft here, we have a disc here, right? And this disc is spinning about the shaft in this direction, okay. It is spin. So the angular velocity is omega, right? Now we have three axes: x-axis, this is y-axis, and this is z-axis, okay. Now if it is already spinning about x-axis, okay, now if we ourselves, if I give a spin about y-axis to this one, okay, or about this axis, whatever, wherever you want to give the spin, I mean, see, one axis it is already spinning about, another axis you have to give a spin yourself, okay. Just that means how to give a spin about this y-axis is like this, okay. This is the y-axis. To make the disc this thing right like this, okay, this kind of thing, this kind, okay, a little bit spin about y-axis. So in that case, what will happen, that finally you will observe that there is a spin automatically that occurs about the axis, okay. Right now forget about the directions, but we need to see the directions later on, okay. So these are the, I mean we have to, we will actually see what are the directions of all these. Now the thing is, this happens because of gyroscopic effect, okay, gyroscopic effect. So when you give a spin, and when a spinning wheel or spinning any spinning object is given a spin perpendicular about its axis, which is perpendicular to its axis of spinning, then it will again, there will be a third spin about an axis which is perpendicular to both the previous axis. So this is the axis of rotation, this is the perpendicular axis to axis of rotation, and we have a third perpendicular axis to that. So if one body is already spinning about one of the axis, if you give the spin about one more perpendicular axis, then it will spin about a third perpendicular axis, okay. So now you see angular velocity, we need to actually now see the vector diagram of this. Now actually what you know that for a vector, for any vector, we just show it with a straight line, okay. So a vector is shown with straight line only, okay, not a curved line. We don't show a vector like this, or a curve. Any curve is not shown in the vector. But in this case you see velocity, linear velocity is linear in this direction. A straight line can be shown for linear velocity, for acceleration, but for angular velocity, since it is changing like this, okay, how to represent a vector of this angular velocity, that we will see now, okay. Now you see this is omega, okay, this is going in this direction, fine, all right. So what you have to do is, you imagine, you just have a look at your right hand. You have to use as something called right hand thumb rule, okay, right hand thumb rule. So here what you do right now, it is difficult for me to place, but you see this one, okay, let me draw a hand, okay. Actually I have it actually already. See here, this is a disc, okay, disc is spinning about this axis, right? So you just place your fingers, okay, four fingers which are other than your thumb, okay, other four fingers in the direction of this rotation. That means in case of this one, this is how your right hand will look like. So the thing is, uh, these are four fingers, okay, and this is your thumb. Are you getting? This is the thumb direction, and these are the fingers. The fingers will curl in the direction of rotation. Okay, in this. So here you can see these are the fingers. See, fingers are actually curling in this direction, right? So you have to put your fingers in the direction of rotation, and your thumb will show you the vector direction. Okay, this is how we have to do. So in this case, look at this. If you place your thumbs and so not thumb, the other fingers in the direction that your fingers going to curl, okay, then your thumb will show. Just imagine other fingers, I mean one to the first, second, third, fourth, all the fingers, if you show this in this direction, then your thumb will be in this direction. Okay, so this is the vector for this. See, so this system can be replaced by a vector AB. Okay, because this is rotating in this direction. So we have to show both this rotation plus this vector. Okay, now if it rotates in the opposite direction, you see, if it rotates in this direction, then your vector direction will be in this direction. Okay, because you just try to place your curl of your other fingers in this direction, so thumb will be in this direction. So this will show you the direction of this vector. Okay, now we need to also analyze the angular acceleration. So here we have this x-axis. So this is a disk which is spinning about x-axis already. Now we have given it a rotation about this z-axis. Okay. Now let's say this is z-axis. Now there's a perpendicular axis. This y is there. Okay. So what will happen? It will rotate about y like this. Okay. So that is the precession. Your gyroscopic effect will be there. So let's consider that we have actually given it a spin of very small angle del theta from x to x dash. Okay, this axis is x and this one is x dash. So this is omega. This is omega plus del omega. Okay, now you read them, that you see we can find out the total angular acceleration of this one. Okay, this disk that is given by d omega by dt plus omega into d theta by dt. Okay, and here you can see d omega by dt is actually the linear acceleration. See, this is the change in magnitude of angular velocity. That means change in angular velocity means only the angular acceleration only, and this is actually omega d theta by dt is the change in the direction of axis of spin. So this is the axis of spin, and change in the direction in the axis of spin. What, see, this omega plus d omega, see, omega is there, omega changes to some more value, omega was there already, plus del omega. If we give it a spin, then this may increase, okay, or decrease, something, some changes will happen. Okay, so d omega into d theta by dt is the change in the direction of the in our axis of spin here. Now actually to understand this thing, no, so this one you have to place your right hand. Okay, and if you place your right hand, thumb direction will be in this direction, and here also it will be in this direction. So this vector will change with respect to this vector. Okay, this vector is more. So now that is the change in the direction of axis of spin. Now let's look at the gyroscopic torque. Okay, so here you see this is x-axis. There's a disk which is spinning about this axis A, and with a angular velocity of omega. And here there's another axis x dash. Okay, now let's keep their angular velocity same. In this case, we will just, if you draw the vector diagram of this, see, this is O, this is A. Okay, so by placing your fingers of your right hand in this curly direction, the thumb will point in this direction. So this is the direct vector OA. We'll show it like this. Okay, similarly for this one, if we give it a spin about z from A to from the position A, it goes to new position B. Okay, then this will the vector direction will be in this direction. So we will show it here. Okay, so their subtraction in this case will be BA, vector BA, if we connect these two. Okay, so this is a subtraction. Actually this is not the addition, because we have to, if we want to add them, then we have to take this OB vector here. Okay, then we join, then will be addition, add, then we can add them. This is the subtraction, OA and OB. Subtraction vector is this. Okay, now uh, just understand this gyroscopic torque. If I is the moment of inertia of a rotor, that means this disk. If I is the moment of inertia of this disk, okay, and omega is the angular velocity of this disk, then when axis of spin takes a turn about z-axis with the angle del theta and time del t. You see, this is already spinning about x-axis. Okay, with it has a moment of inertia of I, it has an angular velocity of omega, and it takes a turn about z-axis. This turn, this kind of turn it takes, and there is the change in angle is del theta, and the time is del t. Now the angular acceleration is found to be alpha equal to omega into del theta by del t. Okay, so this you know, because from here this one, uh, omega into del theta d theta by dt is the change in the direction of spin. So from here is the angular acceleration that we can find out here, from here, because you see linear, this change in velocity remains constant, d omega by dt. D omega by this, omega is same here, omega is same here in both the cases. So change in omega is not there, so that's why this is 0. Okay, omega is a constant in this case. So only we have omega into del theta by d, del t. So for a very small amount of time we can write it as exact differential d theta by dt, omega into d theta by dt, and d theta by dt is actually called the precession. Okay, angular velocity of precession we call. So actually in a simple term, if I say this is the angular velocity about x-axis, and if I give a angular velocity about another axis perpendicular to this, that angular velocity is called angular velocity of precession, omega p, and this is called gyroscopic precession also. Okay, so this is omega, and that is omega p. Omega p is the gyroscopic precision. See, because you see the disk is spinning with omega, this will be very slow. Okay, if I rotate it about another axis, that is the whatever velocity we have for that rotation, we call this as angular velocity of precession. Now here you see this is omega p. We write it as omega p. P means precession, and it is d theta by dt. So ultimately your angular acceleration is alpha equal to omega into omega p. Omega into omega p. Okay. Now the torque we have to find. See, torque is what? I into alpha. Moment of inertia multiplied by this angular acceleration. So if you multiply moment of inertia with this alpha, we get the torque. So torque requirement is the value of couple required to produce a rotation about z-axis. So what extra torque we need to produce this type of rotation about z-axis is actually the angular acceleration about this axis multiplied by your moment of inertia of the system. So I into alpha is the torque that is required to give a precession, or required to give a angular velocity. We call it, term it as omega p. Okay, precession. That means some torque is required to rotate it about z, right? Isn't it? Some torque is required. That torque is actually I into alpha, and this alpha we have found as omega into omega p. Omega is actually the spin velocity of this. It is already spinning about omega, and this omega p is the precession velocity about some perpendicular axis to that axis. Okay, so these are angular velocities. So we can find out this is the this is the couple required to give a spin about that perpendicular axis z. So I into omega p. Okay, so this effect is called gyroscopic effect. Gyroscopic effect. And when you give a gyroscopic effect to this body, this any of them, then we will experience the spin about this axis. Okay. So when as already spinning body about an axis is given a spin about another axis perpendicular to that, then there's a third perpendicular axis to the entire system. It will automatically spin about that third axis. Okay. Now we have found out that the gyroscopic precession is I into omega. Now let's have a look at one numerical. Okay, a uniform disk having a mass of 10 kg and a radius of gyration of 150 mm is mounted on one end of a horizontal arm of 250 mm length. You can just take this system only. Okay, let's draw it here. So a uniform disk, there's a disk, this kind of disk is there. Okay, fine. So which is having a mass of 10 kg is given, and it is connected to an axis. So its radius of gyration is also known for a disk. Since its radius of gyration is known, we and mass is known, we can find out its moment of inertia. How to find moment of inertia? Mass moment of inertia is equal to mass into radius of gyration square. Okay, so this we can find out, and here you can see it is mounted on one end of a horizontal arm. So this is the horizontal arm. It is mounted here. There is some bearing maybe or something is there. It is mounted to that bearing and it can spin about that one. Okay, understood this? So the arm length is given. That is 250 mm from here to here. Okay, this is 250. The other end of the arm can rotate freely in a universal bearing. So there's a bearing, so it can rotate freely. All right. The disc is given a clockwise spin. Now, if you look from this side, then this is given a clockwise spin from your side. Okay. Uh, so from which place you are watching this, that is also important. So clockwise spin of 270 rpm as seen from the disc end of the arm. Okay, so you are not viewing from this side. Disc end of the arm means this is the disc end. This is the starting end. This is the disc end. So you are looking from this side. So for you, the clockwise spin is that direction. Okay, you are standing here. Suppose this is your position. Your standing position, isn't it? So you are viewing from this side means this is your clockwise direction, right? Am I correct? Yeah, this will be the clockwise direction. So this is the spinning rotation for you. Okay, so angular velocity, this is omega. This is omega. Omega is so not omega. This is n. You have to find out omega from here. 270 rpm. From there you find out omega. So omega you can find out from this. Okay. Now what they are asking? Determine the motion of the disk if arm remains horizontal. So if this remains horizontal, determine the motion of the disk. So let's see how to solve it. So in this case, have a look at this. So actually they are asking that what will be the precession velocity here? Precession velocity, omega p, this part. Okay, this part. So now if this part remains horizontal only, this is not going in this direction or in this direction. This actually, if we give it a spin like this about z axis, okay, this kind of rotation is there. Then what will be the velocity of that spin? Omega. Now here you see mass of that disk is given. Okay, length, this is L actually, this is L. Let's take this as L. L is 0.25 meter. K, now K is the radius of gyration, 150 millimeter. We can write it that in meter, that is 0.15 meter. N is 270 rpm. So we can get omega. Omega is 2 pi n by 60. So this is 28.27 radian per second. And moment of inertia I equal to mk square. So mass is 10 kg, k is 0.15 square. So which is equal to 0.225 kg meter square. Okay, this is the moment of inertia. And you know that the torque is equal to I into omega p. So this is torque T. Okay, so T is T or whatever you write, this torque is equal to I into moment of inertia multiplied by alpha. Okay, moment of inertia by multiplied by I alpha. So we can just write it as I alpha equal to oh sorry, we have got that from, sorry, this I into alpha only. This is whatever we are writing. Actually, we need to write down the torque. Sorry about that. So, so you see, very simple thing, that to give this part, this body, a spin about this axis. Where to push? Where do we push it? Actually, exactly to give it a spin, we can push it here also, no problem. Here also, no problem. Okay, but at this axis itself, the disc itself, if you push, okay, here, that will uh, create the proper torque for rotation of this disc. Okay, so here you see mg, actually its weight is there, mg is downward. Okay, now this mg is actually causing a torque. Let me draw it once again. So here is the disc. Okay, and here is the bearing, and here we have the axis. Okay, now its weight is there downward, mg, m the weight, and this is at a distance of small l equal to 250 mm. 250 mm is given, 250 mm length, so that is 0.25 mm. So this is causing a torque already. Okay, now I may be able to explain you this thing. So this is the third axis, right? Let's write, this is y axis, this is z axis, and this is x axis. Okay, so you see, mg multiplied by this length is the moment about y-axis. Okay, it is trying to give a rotation of this disk about y-axis in this manner, because mg is there, this is l is there. So mg multiplied by l is trying to give a rotation of the entire system about y-axis like this. Okay, so this will cause a rotation about z-axis, and that is what is asked. What will be the speed of that rotation? Okay, omega p, about that z-axis, what will be that? That is what you have to find out. So you know now this mg into l is causing what? The couple. So this is causing the couple. So mg into l will be equal to I into omega p, because this couple value is equal to I into omega p, right? So mg into l, mg is the force, its weight multiplied by l is the torque. Actually, we can say here this value of the torque mg into l about this point is trying to rotate the whole um, thing about this y-axis, and because of that we will have a spin about z-axis, and which is given by I into omega p. I mean, this is actually the couple value. So from this we equate mgl equal to I into omega p, and just putting the value, you see, m is 10 kg, z is 9.8, l is given as 0.25, I is, we have found out, 0.225. Here omega is 28.27. Okay, and omega p is, we need to find out. Okay, from here we have got omega p 3.86. So at the end, I'll just you can have a look at this setup here. This is y-axis, this is z-axis, this is x-axis. So this is mg is there. Okay, at a distance of l is there. So if this is a point where it is fixed, you see, obviously this mg is trying to pull the disc down, isn't it? So it will come here in this way, isn't it? This is going to turn about y-axis. See, this is nothing but turning about y-axis, isn't it? This disc is trying to fall, but it cannot fall because it is connected to this point. Okay, so this is going to rotate about y-axis, right? So that means it is already spinning about x-axis. There is another rotation about y-axis, so there will be a rotation because of the gyroscopic effect about z-axis. Okay, and that will be caused by this moment mg into l. Okay, and which is equal to I into omega p from your formula. Okay, this moment, let's call it a moment only, equal to I into omega p. So these two are related like that. So a moment about one axis is related to the value of moment about the other axis as I into omega p. So that is how we have found the value of omega p. That is a precession. That means this disk is rotating about this, its weight is like that, so it will start spinning about z axis with a velocity of 3.86 radian per second, angular velocity of that. Okay, it is very spinning about axis, its speed is very fast, like 28 radian per second. This is the spinning speed about x, and it will slowly spin about z axis like this. Okay, like this, at a velocity of 3.86 radian per second. This is because of its weight is going down, and it is trying to rotate this whole thing in this direction. Okay, so in the coming videos, we will look into its directions. Okay, and and which direction will give you which direction rotation about the axis. So let's read this one. As the disk rotates, the weight of the disk acts downward. Yes, and the couple is created about y-axis. This is what I told, and this is in clockwise direction. The reaction couple tends to keep the arm horizontal, and this is anti-clockwise. Okay, so uh, I mean, ultimately, this if this has to be horizontal, there will be some spinning about the axis. Okay, so that is the thing. So if you have any question, you can ask me, and we will discuss more numerical of gyroscope. Here we have studied only a very few of theory of gyroscope. Okay, a little bit more is required, and we will see more numericals of gyroscope in the coming videos. Okay, thank you.